And so today's speaker is Dr. Lars Borg for Lawrence Livermore National Laboratories, and his focus is on the age of the
A
moon.
couple things to share with you guys. Greg said.
Go ahead, Lars.
Okay, can you guys hear me?
Yes.
Okay, cool. Chip asked me to speak on the age of the moon, which is a paper that I co-wrote with Rick Carlson during COVID, came out in annual reviews not too long ago. And basically, this is a exercise of kind of trying to see the forest through the trees. And so I'm going to run you through the chronology that's been done on the moon and try and show you some of the challenges that are associated with this. Let me see if I can advance the slides. Slides are not advancing. There we go. Okay, so sort of the key points I'd like to emphasize is that the question of the age of the moon is kind of a silly one, because ultimately we measure ages on rocks, and those ages must be interpreted within a geologic context. And so really what we're doing is we're dating a geologic event, and then that event is somehow tied to the age of the body or some key event in its early history. The other thing I'd like to emphasize is that many ages are just simply wrong. And until you do this for a long time and you measure a bunch of wrong ages yourself, it's hard to interpret from just looking at papers. But many ages don't date the event they think they're dating. So for example, if you look at an argon age, it might be interpreted as an igneous crystallization age, but in fact, it represents a metamorphic age. And if you don't recognize that, everything you've done is right. You've just made a misinterpretation of the ages. The other thing that happens is that you often don't date anything. You get an age, but it doesn't relate to any geologic event. And there's a misperception, and I've highlighted in green here, that somehow metamorphism just resets things. And that does happen in some cases. Zircon overgrowth, for example, argon chronology quite readily. But for most isochron systems, metamorphism simply ends up giving you garbage. And so this is a really important thing to understand, because a lot of people say the ages are reset in a way to accept existing ages as somehow meaningful, but that they're reset. And that's typically not the case. Another point that I think is absolutely critical in all this is that the ages need to be evaluated, very critically. We always, as chronologists, we always assess our own isotopic measurements. We look at our uncertainties. We look at the linearity of our lines. If we're doing uranium lead, we look at the concordancy of the sample. We all do that, okay? So that's not really what I'm talking about here. But what we want to do is we want to find other tests. And we can't always apply these, but some that are important, if they can be applied, include things like applying multiple chronometers to individual samples. And in fact, when you're dating lunar crustal rocks, I don't really put a ton of faith in unless you get multiple ages from different systems. The other thing you can do is you can look and see if other labs are getting the same age on the same sample. It turns out this doesn't happen very often, but when it does, it gives you some confidence. And critically, it's important to ensure that the ages are consistent with the petrogenetic framework of the samples that you're dating. So for example, if I date a Faroan anorthosite, which is typically interpreted to be the product of a crystallization of the magma ocean, and I get a billion-year-old age, I should suspect that age, because it requires me to basically rewrite 50 years of petrogenesis of the moon. And maybe that should be done, but that's the consequence of the age. So I'm going to talk about three different types of ages in this talk. The first are going to be absolute ages. These are things you can obtain an age on and tie that material to something critical in the evolution of the moon. The other type of age are model ages. These are less robust because they, of course, require some assumption, about the preconditions under which the moon formed. Usually it assumes that the moon had chondritic abundances of something, but that's not always the case. We're finding out that that assumption is poorer and poorer for different bodies. And the final type of thing I'm going to talk about are ages that sort of only provide a minimum and a maximum. In other words, we've dated this rock, it's from the moon has to be older than this, that sort of thing. So to begin, I'm going to start by putting this talk into the context of some basic geologic models, just so we can sort of get on the same page. I know everybody knows these things, but it's going to be important when I start presenting ages to try and tie them into individual events. So this is a very simplistic model for the origin of the moon. This is pretty much consistent with what we think of today. We think the moon formed as a result of a giant impact between two bodies. We argue about the relative size of these bodies, the velocity, the directness or indirectness of the impact. But the idea is that the impact results in the production of a depleted Earth in terms of size, and basically a breakup of the impactor forming a debris ring. The debris ring is composed of gas and dust, which later accretes to form the moon. The moon accretion involves gravitational heating, which melts the moon, and then it subsequently cools in the context of a magma ocean to form a solid body. So the question given this context is, what does the age of the moon really mean? And as I said, I think it's kind of a nonsensical thing, because for some people, it might involve what the time of the formation of the precursor bodies, the proto-Earth, Theia, what have you. To others, it might be the time of the giant impact. It also might reflect the time that the debris reaccreted after the giant impact itself, or it might reflect the time the moon was melted or the time the moon was solidified. So each one of these individual things and the age of the moon means something different to different people. So perhaps a better question is to ask, what can be dated? And this is absolutely critical, because many of those events, say for example accretion, leave no isotopic record that we can detect that can provide an age constraint. So to determine the age of something, of course, we have to look at samples. And the samples only provide evidence for some different types of events. So there are four main events that I thought of in the context of the paper I mentioned at the beginning that provide some sort of temporal constraint on the age of the moon. The first is evidence from extinct short-lived nuclides. This is one of those chronometers that provides a maximum estimate. If the system is dead when you measure it on the moon, then obviously there's only a certain number of half-lives by which the system can still be preserved, and those half-lives have to have been exceeded in order to get that particular age. Another component that's been talked about a lot is trying to determine the timing of this volatile element loss during the giant impact. There are chronometers that have refractory parents and volatile daughters, and refractory parents. Impacts that involve volatile loss involve the fractionation of the parent and daughter. Using models, we can often constrain the time of the volatile loss. And I'll show you some of the pitfalls associated with this and why I don't think this is going to work for the moon. One of the most robust things we have is solidification of the lunar magma ocean cumulates. We have these materials in our collections, at least we think we do. We can determine ages on these. This provides a time for the solidification of the magma ocean. But again, the moon already formed before this time occurred. So this, in a sense, represents a minimum age. And then finally, there's a series of ages that can be determined using rocks from the moon, particularly secondary crustal rocks, that provide a minimum estimate. In other words, if I date this rock, then the moon has to be older than this point. So I'm going to go through each one of these in order here and just sort of explain where I think these things stand at this point. So this is a chart that just basically shows the four main short-lived isotopic systems that are used to date planetary materials. Now, before somebody gets upset, this isn't all of them. I've chosen these simply because they represent the largest span of time over which we're interested in. So in the very short scale, there's the aluminum magnesium system. It's on the top row here of this chart. It has a half-life of about 700,000 years. Below that is manganese chrome, which has a half-life of about 4 million years. Hafnium tungsten at about 9 million years. And then the samarium 146 and the neodymium 142. And I've put in 85 million years. And if anybody's familiar with this system, the canonical value is 103. However, 2 weeks ago, we've finalized some counting experiments, and this is the number that we came up with. Regardless, it's not going to make a huge difference in the story I'm going to present. On the right-hand side of this graph are a series of circles in columns associated with different materials and bodies that have formed in the solar system. So the first is differentiated asteroids, then Mars, and Moon, and Earth. So for something like differentiated asteroids, we see evidence for live aluminum-26. And so that basically tells us that these things are evolving in the time frame of roughly 5 to 7 half-lives of the system, which means that these things are undergoing geologic processes within about 5 million years. If we look at manganese chrome, again, we just see no evidence for it being live on Mars, Moon, or Earth. And so these bodies had to undergo geologic processes that would fractionate these elements from one another after about 4.54 billion years. Hafnium tungsten is actually a really critical one for understanding the age of the moon, because if we look at lunar rocks, we see no evidence for live hafnium 182. And that means that the elemental processes or geologic processes that fractionated these elements in lunar rocks must have occurred after 4.49 billion years. So this is a hard stop for the age of the moon. I don't see how we can get around this particular value. So that's a really powerful constraint from this system. The samarium neodymium system is basically live at some level on every body, and so it can't provide any sort of hard stop like hafnium tungsten can, but it can be used, and I'll show you in a minute how to constrain the timing of geologic events on the moon. So the second thing that you can use to try and constrain the age of a body like the moon, particularly in the context of a giant impact, is the time that volatiles were lost. And one of the systems that's really powerful in this regard is the rubidium-strontium system. Rubidium decays to strontium. It's a moderately volatile element. It has a condensation temperature, 50% condensation temperature, a little under 600 degrees Celsius. And it decays to a refractory element, strontium, which is effectively unaffected by heating and cooling. So you can look at the strontium isotopic composition of a material and assume that it evolved from in a planetary body along a common evolution path, and you can calculate when that volatilization depletion had to occur. And that's illustrated on this image on the left. This is an age versus strontium isotopic plot. Solar system initial value is represented by the yellow dot here. Based on what we know from chondritic meteorites, we think the solar system evolves along this white line, something like that. If we measured the isotopic composition of rocks on the moon, which might be represented by this red circle and this blue oval here, and we know the parent-daughter, the rubidium-strontium ratio of the moon, we can back calculate the growth of the bulk moon until it intercepts this chondritic evolution line, and then we can drop a line down and we can calculate an age at which the volatile elements were depleted on the moon. And in this case, I've chosen about 4.49 because that coincides with the hafnium tungsten age. The problem with using this for the moon is that the lunar rocks don't lie up where they are on this particular plot, but instead they lay way down here like this. The moon has strontium isotopic composition at about 4.3 billion years that is only marginally evolved from the initial solar system value. And what that means is that the materials that the moon is derived from were never in a reservoir, or were in a reservoir with bulk solar system values for only a very, very limited period of time. And in fact, if you do the calculation, it's about 2 million years. So if you're going to use this to date the giant impact has to occur at about 4.566 billion years. And that's simply too young, because we think accretion of planetary bodies the size of the moon and Theia take longer than that. As a consequence, this model that we're using to date these volatile element depletions is incorrect. And probably what we think it's reflecting is the fact that the materials that the moon is derived from are not bulk solar system values. The moon is derived from a material that was already depleted in volatile elements. And so the hypothesis that we can obtain an age from volatile element depletion of the moon is predicated on the materials that the moon being derived from having roughly solar system average volatile element abundances. And this data indicate that it doesn't, that's probably incorrect. As a result, age constraints from volatile element depletion are problematic. So the other possibility, and the way that we primarily date bodies like the moon, is magma ocean crystallization after accretion and initial melting of the moon start with core formation, followed by silicate differentiation, then mantle overturn, and basaltic magmatism. And I use all of these here because each one of these has some relevance to the chronology that I'm going to present in the next few slides. One point I'll note, however, is that much like the volatile element problem, in which we don't know the starting composition, understanding the timing of core formation is very problematic. And the reason is that we think bodies accrete from smaller bodies, and that accretion process is not necessarily a closed system. And because these bodies are often differentiated and contain cores and are potentially fractionated by impacts and giant impacts, it's very difficult to constrain core formation processes. And so these become so highly model dependent that, in my view, they don't really provide a very robust constraint on the age of core formation or secondary core formation on something like the moon. Okay, so I'm going to spend a couple of minutes in a very simplistic, albeit almost stupid sense, talking about what we think of for the crystallization of magma oceans. And I'm going to use the moon as an example here. But at the end of this, what I'm going to try and show you is that in this conceptual model, there are several materials that can actually be dated via absolute ages or model ages, and those can be used to constrain the time of crystallization of the magma ocean, which does provide a pinning point for the evolution of the moon. So in this cartoon is a picture of sort of a hypothetical magma ocean that's crystallizing. It crystallizes down a liquid line of descent. Most people want this to be anhydrous and essentially at very low pressure, so it has a very simple mineralogy. Olivine is the main liquidous phase that crystallizes initially, followed by orthopyroxene, followed by plagioclase. By the time plagioclase crystallizes, the remaining liquid is depleted in magnesium and hence enriched in iron. As a consequence, plagioclase tends to float, forming a crust. In this particular cartoon, note that the plagioclase-rich crust is way overrepresented in terms of its thickness. After plagioclase crystallizes, more mafic silicates begin to crystallize. These typically have higher iron contents and are more dense. Clinopyroxene is one of the main phases there. And finally, after maybe 95 or maybe even 98% crystallization of magma ocean, something like ilmenite starts to precipitate out, which contains iron and titanium. And then there's this sludge that's left over that contains everything that doesn't go into any of these minerals. So it's going to be enriched in all of the traditionally incompatible elements. And as a consequence, it has the unimaginative name of creep, standing for potassium, rarus, and phosphorus. The thing to note here, I've put the density of these various minerals on this plot, and you can see that we've got a inverse density stratification here, where things like ilmenite are the most dense, and they're at the top, and things like olivine and orthopyroxene are the least dense, and they're at the bottom. So given that there's a gravity instability, it's been suggested that there was a period of mantle convection called overturn, in which the denser material sinks to the bottom and the more buoyant material rises to the top. Note that plagioclase is expected to stay on the surface because regardless, it's going to be more buoyant than any of the mafic minerals below it. And likewise, creep-rich material is probably going to migrate upwards during this because it also is relatively buoyant. And because it has radioactive elements, it may also still be hot. It may even be partially liquid. The next stage in this evolution is a period of secondary crust formation. The main crust that the main rock type that we see are rocks belonging to the magnesian suite. As most of you, I'm sure, know, these are primarily found at the 14, 15, and dominantly at the 17 sites. These rocks contain olivine and pyroxene, plagioclase, and have a fairly large enrichment in incompatible elements. And so they're thought to form as a result of some sort of interaction of primary magma ocean cumulates during perhaps associated with the overturn event that I just talked about. The magnesium suite has a cousin called the alkali suite. Justin is going to talk a fair bit about it tomorrow, but basically these are rocks that have a similar petrogenesis. They're significantly more evolved in terms of silica contents and what have you, but they have a very strong incompatible element enriched signature as well. Exact relationship of creep and magnesium suite is not well understood, but the point is that there's a batch of secondary crustal material that's thought to form after crystallization of the magma ocean. And if this material is dated, it provides a minimum age for the timing of magma ocean crystallization. The final thing that happens is there's a series of basaltic rocks that are formed as a result of melting in the mantle and are erupted onto the surface. And this is important because these materials can be used to sample the interior of the lunar mantle. So looking at this scenario that I just presented, what are the things that can possibly be dated? So I've listed them in the order that we think they form in 1 through 4. Number 1 is the mafic cumulates, which are thought to be some of the first things that form out of the magma ocean. These are represented by the basalts that are erupted on the surface and are ubiquitous in the Apollo collections. The second thing that's thought to form is the phroanorthosite crust. This is material that we have predominantly from the Apollo 16 site. I've shown an image of this to emphasize the fact that most of these rocks look pretty beat up when you get them, and this is relevant to the chronology. The third thing that is thought to form is creep. Creep is represented as a component in various rock types, mostly in breccias. The only places that we see it in igneous samples are in creep basalts, magnesian suite, and alkali suite rocks. And then the final thing that we see are these secondary crustal rocks, norites, gabbronorites, troctolites, dunites, and things like that that are erupted into the crust. So I'm going to go through the next few slides and show you some ages that have been determined on these various materials. And these are going to be a variety of model ages and absolute ages. These are, get the camera focused where I'm looking. These are rather complicated scenarios in some cases for the generation of these model ages, and I don't have enough time to go in and talk about how they're all generated, so I'm going to gloss over this a little bit and just try and give you enough information that perhaps you might believe me. Okay, so the way you date mantle rocks is by looking at the isotopic systematics of the Mare basalts. You take advantage here of the fact that the moon crystallized fairly early, the magma ocean crystallized fairly early, so that there are two live chronometers at the time that this formed. The first is neodymium-146, which decays to neodymium-142, has a half-life, as I said earlier, of about 85 million years, I think. And then there's a longer lived system that has a half-life of about 106 billion years and is active today. Basically, what you do is you measure the neodymium isotopic systematics of the Mare basalts, and that effectively gives you an understanding of what the neodymium-142 value was as their source regions. Then you use the long-lived system to calculate the samarium-neodymium ratio of the sources. And you plot it on a diagram like this, in which you have the samarium neodymium ratio of the source. In this case, it's represented in isotopic form because it's easier for the calculations, against the measured neodymium isotopic compositions of the rocks. Turns out the slope of this line is proportional to the samarium-146, neodymium-144 ratio that was inherited into the magmas from which these rocks were formed. That in turn defines an age of about 4.37 billion years. The point to note here is that this, in a sense, is confirmation that the magma ocean model is correct, because all of these rocks lie on a single line. And the fact that that is such means that they all are derived from essentially a common parental melt, as is consistent with the magma ocean model. But there are other magma ocean cumulates that exist, and they should also lie on this line. Those magma ocean cumulates that I'm talking about are pharonornithocytes. The measurements of 142 in pharonornithocytes is much more difficult than in basalts because there's much less neodymium. Nevertheless, the three rocks that we've dated, as well as for 142, as well as rocks that have been analyzed by Boyette et al., all lie on the same 142 isochron line, indicating that all of these rocks, all the mafic cumulates, which include high titanium and low titanium rocks, as well as the pharonornithocytes, are A, derived from a common parent, and B, derived at a time at about 4.37 billion years. So this actually is one of the most robust ages that we have for the formation of the moon. But we can also throw ourselves futilely in the attempt to try and date pharonornithocytes. And I've spent a fair bit of time doing this. I think I've worked on about 6 of these things now. These are the 3 best ages that we have so far. The first is pharonornithocyte 60025. This rock was analyzed in conjunction with Jim Connolly and Rick Carlson, where we obtained concordant RBSR and uranium lead ages. The age of this particular rock is probably the best defined of any of them. And if you look at the weighted average, it's about 4.36 plus or minus about 2 million years. So it's very, very well-defined age. All isotopic systematics of all these rocks look reasonable with their petrogenesis. Most of these rocks have been dated by the 142 and the 143 system and are concordant. So I have confidence that they're correct. The samples themselves are on the right-hand side, and I'm showing you these to illustrate the fact that these are really difficult materials to work with. If you look at the 60025 sample on the upper right, you can see that there's huge amounts of pyroxene. That's what enabled us to get such good uranium lead ages on it. But if you look closely, you'll see a whole bunch of black veining cutting through this rock. That's impact melt. And if you look at all these rocks in detail, you'll see that there's evidence for impact melt cutting through them. If that gets in your sample, you don't get a good age. So these rocks are incredibly difficult to deal with. Nevertheless, if you look at the ages that we've got, we have a sort of an average age showing up here at about 4.3 billion years. However, there are other ages that have been determined. Some of them are even ages that I've been associated with that don't seem to behave quite as neatly. They are typically dated by only one system. They show ages that are either anomalously young or anomalously old. And so this is the total set of ages that have been dated. And you can see that some of them are very old. Some of them are as old as the solar system. You can see that ages from different studies sometimes don't agree. So Rick worked on both of these 60025 samples together, and yet they differ outside analytical uncertainty by almost 100 million years. If you take these ages all at face value, it implies that Frohn northite production occurred over about 250 million years, which even for people who want the moon to cool slowly becomes problematic. If we look at just the ages that have been determined by multiple chronometers, they still span almost 120 million years. So clearly there's a lot of issues here that we don't understand. One of those issues is that the ages of slowly cooled rocks are affected by the cooling rates that they experience. So if you look at the photographs or the images that I'm showing for one of these Frohn orthosites, which was a clast from 60016. This is a rock that yielded an age of about 4.3 billion years. And you look at the lower right on this diagram, you can see that these minerals are homogeneous. They have poikilotic textures. They show pyroxene neck solution. This material clearly shows evidence that these rocks cooled extremely slowly. This rock has coincidentally, one of the youngest crystallization ages of all the Frohn orthosites at 4.3. It also has concordant argon, and SMD ages. And so if this rock cools slowly, there's no reason to expect that these two chronometers should yield concordant ages, because argon closes at about 500 degrees C in the Frohn orthosite, and samarium neodymium closes at about 900 degrees C. And so if these rocks cooled very slowly, we would expect to see discordancy between these two ages. So the fact that these ages are concordant probably means that we're not dating the emplacement event of this particular rock into the crust, but rather we're dating the time that it was exhumed out of the crust onto the surface and then quenched. Slow cooling is also illustrated on this diagram. This is a diagram that I produced associated with cooling of the troctolite 76535. This is one of the slowest cooled rocks we have from the moon. And what we noticed was that we determined a variety of ages by samarium neodymium, rubidium strontium, lead, and argon, and they all differed, and that they got progressively younger as the closure temperature of the system got lower. And so what it turns out, we think what we're looking at here is a cooling history of this rock. So if you look at the circle on the lower right of this diagram, that's the argon age. It blocks at about 500 degrees C. That's essentially the time it's locked in. Rubidium strontium and lead and plagioclase lock in at about 650 degrees C. And then in this rock, samarium neodymium locks in at about 825. So if you regress a line through here, that effectively is the best estimate we can make of a cooling rate, and look when that line intersects the solidus of this particular rock. We could argue that although our SMD age is about 4.3 billion years, this rock was likely emplaced at its solidus temperature, which would have been about 1100 degrees, and would have corresponded to an age with a maximum value of about 4.38 billion years. So some of the variations we're seeing in these plutonic rocks are reflecting the cooling histories, which are very hard to get your hand around. So the final thing we can date in terms of getting an absolute age for magma oceans involve them determining creep model ages. Creep model ages have been in the literature for many, many years. I think Carlson and Lugmeyer put out the first creep model age of about 4.36 in 1978. These models basically estimate when you have to fractionate samarium from neodymium, because they're samarium neodymium model ages, from a chondritic reservoir in order to generate the isotopic systematics you see in a particular rock. A graduate student of mine published a paper about 10 years ago where we used a TI diagram, which is the age versus the initial isotopic composition measured on rocks, to calculate the model age using a regression. This has the advantage that it provides an internal test for the validity of the model. And I've shown you a couple of these. So for the moment, if you look at the lower diagram on the right, these are various creep-rich rocks, creep basalts, magnesium sweet rocks that have been dated. And they're plotted on this diagram with their age versus the initial neodymium isotopic composition. The yellow horizontal line going across the diagram is effectively the evolution of an undifferentiated body like a chondrite as it would evolve through time. The various rocks that are sampled lie on a line that deviate from this. This stems from the fact that the rare earth element systematics in creep-rich samples are effectively dominated by the creep. As a consequence, the isotopic composition and systematics of these individual samples basically gives us a point in time for the evolution of creep. So with that in mind, a line can be regressed through this data, and where it intercepts the chondritic evolution line defines an age. For SMND, the age that is calculated here is about 4.39 billion years. If you do the same thing for lutetium hafnium, you have an age of about 4.35 billion years. And these are essentially in agreement with one another. So the question that I always get asked has to do with the zircon age that was published in about 2017. And I'm just showing it in the context of the whole rock data. So zircons are thought to be derived from creep-rich rocks that are similar to the rocks that define the whole rock isochron, which is represented here by this red line with these 3 dots, as well as data that were analyzed by Peter Sprung in 2013. And you can see that the zircon ages or the zircon data fall all over the place, and we don't really know why this is. But the bottom line is that the regression analysis that I just showed you can't be applied to these rocks because they're not linear. Just like on an isochron, if you have scatter on the diagram, you can't regress a line through it. The power of this approach, however, is that the line that you regress through the sample is the slope is proportional to the lutetium hafnium ratio, in this case, of the source material. And the source material here is creep. So since we have a vague idea of what the lutetium hafnium ratio of creep should be, we can compare the regression that we make through the rocks with the lutetium hafnium ratio that's estimated for creep. So in this case, for the rock data, we have a value of about 0.015. Creep has a value of about 0.018. So the fact that these two values are roughly agreeing is giving us confidence that we're actually dating the time of creep formation. So where do we stand on all of the chronology we have so far? So this is a list of all the crustal chronology that we've generated for both the ferronornithocytes and the magnesium suite. And you can see that it's kind of a mess. Just like the ferronornithocytes, some of the ages that have been determined on secondary materials that provide a minimum age for crystallization of the magma ocean are really old. Some of these are actually as old as the solar system. The other thing I want to point out is that ages from different studies often don't agree. The color codes here on the diagram here are indicate samples that have been dated by multiple labs at different times. And you can see that they really don't agree. So for example, if you look at the 67667 sample that was done by Carlson and Lugmeyer in, I think it was 82, it differs very, very significantly from the values that we put out just a little while ago. And so these ages have to be viewed with a lot of trepidation. Nevertheless, it looks like both of these rock suites are essentially contemporaneous with one another, which of course challenges our understanding of the magma ocean model. So we clearly have some picking and choosing to do here, or we can abandon what we think of as the traditional magma ocean model. And I'll get into this in a little bit more detail in a minute. Detrital zircons are another way that we can constrain the age of alkali suite magmatism. These are basically zircons that originated most likely in alkali suite rocks. There are a few zircons that you see in magnesian suites, but they're rare. And the rocks have been basically broken up by impacts. And so these zircons are effectively detrital and breccias. And this is a histogram I made a few years ago showing a summary of the ages. There's a few more ages now, but basically the age range goes from about 3.82 to about 4.46 and there's a pronounced peak at about 4.34 billion years. And so the question that one needs to ask oneself with regards to these is what are they recording? The fact that there's a peak at about 4.34, and this is in pretty good agreement with what we think are the best ages for photonorthocytes and match the model age reasonably well for the crystallization of the mafic cumulates in the lunar magma ocean, suggests that this is probably representing an igneous event. And this igneous event is widespread because it's recorded in mantle rocks and crustal rocks, and it's seen all over the place. But what do the rest of the ages mean? The fact that the ages end at about 3.8 billion years probably means that we're recording the Imbrium impact here, or at least late impacts. And so we're getting some resetting of these zircons as a result of impact events. But the question is are all of these ages recording events, or are some of them simply reflecting some disturbance? Or is it some combination? And the answer, of course, is it's some combination. But that makes interpreting these things rather difficult. And so there's not really a clear insight that can be gained by looking at these, because there's nothing else other than a single measurement on a single grain. There's no collaboratory measurements can be made. It's very difficult to evaluate the petrogenesis. And so it's problematic. So in summary, if you look at all the ages that we have, we don't really have a very good time constraint on the age of the moon if we look at all these values. If you look at the hafnium age, we know the moon is younger than about 4.49. We look at the mafic cumulates, which is probably our most robust age. We have an understanding that it has to be the age of the mafic cumulate formation is somewhere around 437, 438. We look at the ages of the photonorthocytes. They span a range from the beginning of the solar system to about 4.3 billion years. Ore creep ages, if we use the age defined by the zircons at 4.5 billion years, and we use youngest ages that have been determined through regression analysis at about 4.35 billion years, we have a rather large range of 150 million years there. The magnesian suite rocks, again, taking all the data at face value, go from about 4.51 to about 4.2. And finally, the detrital zircons go from about 4.46 all the way down to 3.8. And so given the chronology, taking it all at face value, it doesn't work. And so here's what you basically have. You either have a lunar magma ocean model that's no good, and that we've totally missed the idea of having a magma ocean, flotation cumulates, formation of creep, all of this has to be rewritten, or maybe not all these ages are right. And as I said in the very beginning, the answer is the latter. So how do we address this? What you need to do is you need to start thinking about the systematics of suites of rocks. And so in the next few slides, I'm going to try and show you this. So if we look at all the isotopic data that have been completed on pharoin and orthosites, and we use them to define a single age, this is a model age, albeit, but what we're saying here is we're saying that all of these anorthositic rocks should be derived from a common magma at a common time. And if that's true, then a line regress through these should provide the best estimate we have for the crystallization of the suite as a whole. And so in this case, when we do this using something like 7 or 8 different pharoin anorthosites, note that one is even not from Apollo 16 site, we have an age of about 4.37 plus or minus about 30 million years. And this is probably the best age we're going to get on the pharoin anorthosites with the current data that we have. Coincidentally, this age is almost completely concordant with the lead age that we determined on 60025. If we extrapolate that age for slow crystallization, the age we have there is 4.384 plus or minus about 2 million years. So we're seeing a consistency there. So taking this and going through all the different rocks that we have and trying to summarize and paint some sort of coherent picture, end up with a series of ages that look something like this. The zircon distribution is shown in the background. The first thing we think that should crystallize from a magma ocean is the Mare basalts. They have an age of about 437. Average anorthosites, about 437. The best anorthosite, 438. Average model creep ages using only the regression analysis is about 436. We use the average ages determined on magnesian sweet rocks. These are ages that have been determined by multiple systems and multiple labs. They also come in and around the 433 to 432 kind of time range. And then this correlates very well with the peak in zircon ages. So putting all this together, the best ages that we have come down to something like this, and you can see that there's a relatively tight pattern that is presented here. And if we take the average of all these things, we end up with an average age of about 437 plus or minus about 30 million years. And this is the best I think we can do at this current time. Keep in mind, however, that this doesn't mean this is the time the moon formed. This is the time we think the magma, or I think the magma ocean crystallized. So, final slide, just to reiterate some of the things I've said. Chronometers only date specific events that fractionate parent and daughter. And therefore, it's critical to understand the fractionation process, in other words, the geologic evolution of the material that you're measuring, before you can constrain the significance of the age. The only planetary scale event that we seem to be able to date is the crystallization of the magma ocean. Core formation, volatile element depletion is just something that is too model dependent to provide anything that I can really trust. The evidence for such a global event, however, should be ubiquitous. If we're calling on crystallization of a global magma ocean, we should see evidence for that age everywhere. And in fact, we do. And so that gives me confidence that we're actually dating the thing that we think we're dating. But we must keep in mind that many, and I would argue even most, ages that have been determined on lunar samples are probably unreliable. And so they have to be viewed with huge amounts of skepticism. The only way you can address this is by checking the reliability of the ages. And you can do this by applying multiple isotopic systems to individual samples and more importantly, is you look at the consistency of the age you have with the other ages that have been determined. If you end up with an age that's unrealistic, you have to evaluate what that means for the other ages. And just saying that they're reset, quite frankly, is not right. It's you can't reset ages very often. And so those ages are either meaningless and you're just unlucky, or your age is meaningless and you're just unlucky. But that's basically the hard truth of it. And so if you look at all the ages and whatnot, and you calculate all the uncertainties, the best age for the moon, the solidification of the magma ocean with all the caveats I've explained is about 4.38. Thank you.
Any questions for Lars? Carl?
I don't know if you can hear me, Lars. Carl Agee here in 340. Can you hear me?
Yeah, I got you.
Great. I think you may have talked about this maybe in that last teleconference, but all the Apollo samples are from the near side, and so there's this assumption that everything is from the magma ocean. But what if you're looking at a biased sampling that is influenced by near side, basin Burming impacts and et cetera, and that maybe far side samples are going to give you different ages?
Yeah, of course, the samples we are looking at are biased, right? I mean, that's a foregone conclusion. However, if you look at something like the neodymium-142 isochron and what it's encompassing rocks from all over the sampled area, which go from basically Apollo 12 to Apollo 17, which is something like 1,700 kilometers across. Plus, they're sampling material down to the bottom of the mantle where basalts are extracted from. And we argue about how deep that is, but that's probably also maybe up to 500 or 800 kilometers in depth. And so if you just sort of take a volume of the moon there that's represented by that, it's something like 15 to 20% of the volume of the moon. And that's what's being recorded just in that simple isochron. And so if you want to call upon some sort of secondary process like an impact, you have to melt that rough volume of the body. Not impossible, but I would expect that to be a very obvious thing to see. And the fact that we don't see it leads me to believe that we're probably sampling something that's representative of the bulk moon. Of course, until we get samples from the backside, we don't know that. One point I'll add to this is that some of the ages that have been determined in isotopic systematics that have been determined on meteorite samples also fall on that same isochron. Now, they may be from the near side too, we don't know, but it's not just the Apollo collection, although it is dominated by that, and that's a concern.
Great, thank you, Lars. Ricky, do we have any online questions?
I have a question, if you can hear me.
Yes.
I can.
This is Zach Sharp. Very nice, Lars. Wonderful talk. My question relates to something that is almost peripheral here. You talked about the rubidium strontium age, that it was too old, that it was just a few million years. And there's now a lot of people working on pebble accretion as a mechanism to form the planets. And 2 million years is actually quite within the age for making a planet by this mechanism. So I realize that there's also, you talked about the short-lived isotope anomalies that aren't there, but I think that it's, a little problematic to reject the RBSR simply because the age is old. When you were giving your presentation and you said they're really old, I thought, oh, well, they should be about 2 million years. And then that's what you said. So any comments or thoughts?
Yeah, I'm not talking about when planets form. I'm talking about when the giant impact occurs. So you can form Theia.
Wait, no. But the 2 million year thing, wasn't that was extrapolating it back to the chondrite bulk solar system age.
Right. But that is, if if rubidium strontium is evolving along a solar system evolution model, and you have two bodies that form with basically chondritic abundances of rubidium and strontium, you have to remove that rubidium at that time.
Oh, okay. So that's the
So that's the
the
time
impact age, 2
that's
million
the
years.
giant impact age.
Oh yeah,
And so
okay.
if you want a giant impact at 2 million
No,
years,
never
you've
mind.
got to form Theia and the proto-Earth at that point, and then you have to explain why there's no live short-lived
No,
isotopes on
Yeah,
any
no,
of these
I was
bodies.
talking about the precursors, Lars, not the impact. So yeah, okay. Never mind then, my mistake.
Yeah, so we wrote a paper last year, I think, in PNAS, and what we argued is that I think the giant impact probably is not responsible for the volatile element depletion in the Earth-Moon system. The volatile element depletion that we see is just a function of the fact is that's what the materials that the proto-Earth and Theia formed from looked like when they formed.
Thank you, Lars. Ricky, do we have any online questions?
There are two questions, Chip. This is
Okay.
Justin. There are three actually, but there are two. One is related to actual sampling and whether it might be useful, given sort of the disturbances at the nearest near surface, to sample at a greater depth than we have before. So, several meters depth if possible. Then the second one is I think a really interesting, important, but obviously, as the questioner states, a little bit foolish, which is, you throw out all these reset ages, if you will, because you don't get metamorphism that causes reset ages. But everything is a series of resetting. So, solar system formation is an event, and then forming the planets is resetting, if you will. So the question basically is, why don't you just always get the solar system formation age, or even further back?
Okay, I think let me address the second question first.
Yep.
Resetting in the context of what the questioner is asking is not really what I meant by resetting. What I mean by resetting is you have a rock that shows every evidence for being a rock, and it has certain characteristics that you invoke to reflect some petrogenetic history, but the age is problematic. It's too old or too young or something like that. And so what you do is you say, well, the age was reset. So I'm going to use all the petrographic characterizations of this rock to explain how, maybe a magma ocean works or how alkali sweet evolve or something like that. But I'm going to discard the age because it's been quote unquote reset by some metamorphic event. And the point that I'm trying to make is that you don't get that kind of resetting and still preserve the original characteristics of the rock. Now, if you melt the whole bloody thing, then yes, technically that's resetting, and it is from the standpoint of evolution of isotopes in the history of the solar system. But really what that is that's basically wiping the slate clean, and that's starting from fresh. And so if you totally melt something and then you recrystallize it, you date that material, you know that you're dating that recrystallization event or a crystallization event. You may not know it's a recrystallization event. So in that sense, it's a little bit matter of what you mean by resetting, but resetting is sort of the coward's way out of explaining chronology that you don't like. And so having seen a lot of scatter in the isochron plots I've generated, I realize that what you're always trying to do is you're trying to see through disturbances. In some cases you can, in some cases you can't. And the prime test for seeing through that is concordancy from multiple systems. So that I give you that as my way of perception. From the standpoint of depth, the problem with the depth is that the processes that are affecting these rocks, impact metamorphism, and I didn't mention it, capture of thermal and epithermal neutrons, occurs at depths that are difficult to sample below. An impact basin, it may be extracting material from 20 kilometers or something like that. And so just drilling down into the megabreccia of the lunar surface is probably not going to allow you to get away from looking at these problems of resetting or disturbance and metamorphism. You can go to different areas, of course. So, for example, if you look at Mare basalts, they're relatively easy to date because they haven't seen any of the impact history that the older rocks are. But as far as addressing the question of how old is the moon and when did the magma ocean solidify, you really have to go into the lion's den here to address the question of how you see through prevalent impact metamorphism on the moon. And I can't emphasize this enough. There's nothing on the Earth that has seen the extent of metamorphism that lunar highland crustal rocks have. They're just destroyed, and so it's a battle that everybody fights.
Lars, let's take a couple more questions if we have any. Justin, is there any other questions online?
I see no other questions. Oh, wait.
Okay.
No, there is one that
Any
just jumped up.
from UEM audience?
Could I ask a question, Lars? Can you hear me?
Is that you, Jim? Yeah.
It's me, Jim. Yeah. I'm just wondering if you do not feel that the devolatilization has a significant role in the giant impact in the formation of the moon. Could you comment on what appears to be a greater volatile depletion on the moon relative to Earth?
Yeah. Yeah, I think so. So let me clarify a little bit. I'm not saying that there was no volatile element depletion on the moon. What I'm saying is that the bulk of it probably didn't occur during the giant impact. The fact that the Earth and the moon have different volatile element abundances reflects, I suspect, the fact that the moon is composed mostly of one body and the Earth is composed mostly of the other body. And that those two bodies probably formed in slightly different distances from the sun, maybe at slightly different times when there was different abundances of gas in the protoplanetary disk. So a scenario that we speculated in the PNAS paper I was talking about earlier is that you form Theia, import of the proto-Earth at higher temperatures. It has as a consequence, when it condenses, it has a lower volatile element abundances than the Earth does. And then during the impact, you have a limited amount of mixing between the two bodies. And in fact, there is kind of a hard constraint placed on the rubidium-strontium isotopic compositions of the Earth and the moon that you can only mix about 10% of the Earth into the moon. Because if we look at the rubidium-strontium isotopic evolution of the moon or of the Earth as we think we understand it, it will be too evolved in terms of strontium isotopes to mix with the moon, even if the moon has essentially solar system initial strontium isotopic compositions, and still preserve the low 87, 86 that we observe in lunar rocks.
Yeah, I guess part of the problem comes in is the great similarity between the nucleosynthetic signatures that the moon and the Earth share. If you want to form them at different places and times, essentially, to explain the volatile loss, which corresponds quite well to the different masses. And I see that if you have a two-stage evolution of loss, say you have 80% of the loss early and you allow for some loss later, you don't have much wiggle room if you've got such a low 87-86 ratio. So I see the problem. Yeah,
I don't think it's that big a problem because the temperature gradient near the sun in the T Tauri phase is intense, and yet the volume difference of space is trivial. And so I could see you having very different volatile element abundances and having the exact same isotopic compositions. So
Okay.
I don't see that as being a problem because everything is going to be inboard of where we are now or, something like that. So I don't think from a volumetric standpoint, it's as big a deal as you think you can be as far as nucleosynthetic anomalies. And Jim, we can talk about this offline. If you want to know a problem, I think it's the tungsten isotopes. And I don't have a good explanation for those.
Okay. Thanks.
I could take one more question. Anything out there?
Hey, this is Tab Breslow. Can you guys hear me?
Yes.
Hey,
What's that?
hi, Lars. Great talk. I was curious about your thoughts of the mechanism to sort of explain, this apparent transition from forming the structure of the moon to these episodes. We're kind of pinning that transition time to the MG suite as the first sort of period of secondary crust building or magmatism. And the reason I'm asking is because, obviously we have this overturn mechanism, but then also the recent studies pointing out that the SPA impact itself also sort of becoming older and older with more and more study based on crater density and or crater frequency distributions. And it's also, sort of concordant with these ages around the 4-3-5-ish time period. And so kind of getting your thoughts about the mechanisms or maybe an alternative mechanism to sort of describe these things. Thanks.
Yeah, okay. We've had some conversations on this. Let me see what I can do. So the observation is if you squint your eyes, it looks like the magnesium suite is on the order of about 20 million years younger than what we see for what I take as the crystallization age of the magma ocean. We've dated a variety of these rocks. Unfortunately, they've only been from 2 or 3 sites, and they all seem to be concordant. And so this points to a pulse of magnesium suite magmatism. If you have a pulse of magmatism, now you're looking at a stochastic process. This isn't something that's continually melting of a mantle as a result of radioactive decay or something like that, as you might call for Mare basalts. So now you can start throwing in anything you want to account for this. So if you have an impact at 4.35 that coincides with that, and you can find a physical mechanism to generate the magnesium suite and the alkali suite potentially too, as a result of this, it's completely consistent with the chronology. You could also do this as a result of melting associated with overturn, as you yourself have discussed in some of your papers. And it's very difficult to delineate those two things because there is coincidence. And when you compress the geology to the extent that we're basically calling upon all crustal formation, lunar magma ocean crystallization, and solidification of the body to essentially be compressed within a few tens of millions of years. It's really, really hard to delineate those things. But I don't have a problem with either one of those. My bias is that it seems like overturn seems a more likely mechanism because this is a way to take something that's hot and under some pressure and bring it to the surface, which we know from mid-ocean ridges causes melting. I'm not sure impacting on the far side of a body it necessarily generates, melts on the other side. So I guess off the top of my head, that's sort of my thoughts on it.
Okay, it's 10 after noon right now, at least in Albuquerque. Why don't we go ahead? And I just wanted to thank Lars again for giving this presentation. This was great. Thank you, Lars.
Sure.
And also I just wanted to thank everybody for joining us. And next week we have Dr. Yang Liu from JPL, who will give a presentation that focuses upon the volatiles associated with pyroclastic deposits on the moon. Thank you again all for attending. And Lars, this is terrific. Thank you again.